Welcome! This is the third video in my series Our Star the Sun, and this one describes where the Sun gets its energy from. I've been joined in this effort by my long-term colleague Dr. Julia Saber, and we hope you will enjoy the rest of the series. If you have any comments or questions, please enter them in the comments section below. And if you want to see the other videos in this series, please go to my home page and there should be a playlist there with those videos on it. First, let's take a look at some of the main characteristics of the Sun, which we've established in some of the previous talks that we've given. The Sun is about 4.6 billion years old. Its composition is mainly that of hydrogen. The mass is 2 times 10 to the 30 kilograms, and most of that mass is in the form of plasma, i.e. ionized atoms. And if the Sun is mainly made up of hydrogen, that implies that the Sun is mainly made of protons and electrons. The surface temperature of the Sun is nearly 6,000 degrees Kelvin, and that gives us an output of 3.8 times 10 to the 26 joules, which is increased by about 30% over the lifetime of the Sun so far. The Earth is about 150 million kilometers away from the Sun, and so the Sun warms our surface to about 16 degrees centigrade. Now that's a bit of a mystery, because at the distance that we're currently from the Sun, then our global temperature should be much lower, like about 32 degrees centigrade lower, i.e. we should be an ice planet, and we're not. The main reason for that is the composition of our atmosphere, composed of greenhouse gases like carbon dioxide and water vapor. Over the centuries, there have been many ideas as to where the Sun gets its energy from. Early on, the idea was based on chemical reactions. Then, gravitational collapse was a possibility. Some strange theories had the Sun powered by massive interstellar electrical currents. Then there's the idea of nuclear fission, and now, more recently, nuclear fusion. So we'll take a look at each one of these in turn and see what their various pros and cons were. So can we explain the energy output of the Sun from chemical reactions? The answer is yes, but the problem is, how long will the Sun last if you use chemical reactions to produce the amount of energy that we see coming from the Sun? That's a fairly easy calculation. We know that the solar atmosphere is made up of about 1% of oxygen, or that was equivalent to about 2 times 10 to the 27 tons of oxygen in the Sun. That's a lot of oxygen and could burn up to 6 times 10 to the 25 tons of hydrogen. We know how much energy you get from burning a ton of hydrogen, and we put those figures together, and that would give the potential energy output of the Sun to be 7 times 10 to the 30 joules. We know the rate at which the Sun produces energy, and so if we divide that into that total amount of energy, we get the lifetime of the Sun, and that turns out to be about 10 hours. So chemical reactions by themselves cannot explain the energy coming from the Sun at the current rate. Well, could gravitational collapse be the source of the Sun's energy? As we saw through the process of the Sun's formation, the collapsing gas cloud produced a lot of energy and a lot of heat in the interior of the gas cloud as it collapsed. Could that collapsing process not be continuing? Well, we can check this out by looking at the potential energy and seeing how much of it can be converted to kinetic energy and therefore to heat. If we compare that heat with the production rate of the Sun's energy, we get a time scale, and we can see whether that time scale is consistent with the age of the Sun. Potential energy is the mass of the Sun times the gravitational constant times the radius of the Sun. That turns out to be 3.8 times 10 to the 39 watts. The energy production is about 3.8 times 10 to the 26 joules. Divide one into the other and you get a time scale. So that would come out at about 320,000 years. That's much longer than the chemical theory, but still is not anything like the remote right amount as far as explaining a 4.6 billion year old Sun. There are other objections to it too. If the Sun were continuing to shrink, the spin rate should be increasing, but we're measuring the fact that the Sun's spin rate is decreasing. Also, if the diameter of the sun were shrinking, then the timing of eclipses would change over time. And as far as we can see, that has not happened as yet. There is a theory, at least propagated on YouTube, that the source of the sun's energy is electrical. The model claims that the sun is a giant anode, positively charged, so it attracts interstellar currents of electrons that power the sun. There are many difficult problems associated with this particular model. Here's just 3 of them. First of all, we don't detect any such currents, and they would have to be massive. The solar wind is an outflow of neutral plasma, i.e. charged particles, particularly protons and electrons. If the sun were positively charged, that would pull the electrons back towards the sun and accelerate the protons away from the sun even faster. And we don't see that happening. In order to get any energy from an inflowing electric current, you would have to have something to disperse that energy, or to derive energy from that current. And for that you need a resistance. Now, the resistance of the solar plasma is very low because it is a plasma. The sun is an extraordinarily good conductor, so no amount of inflowing current is going to heat the sun. Another possible source of energy would be nuclear fission. The most common fissionable element in the sun is uranium, and we know from the elemental abundance there's about 1.6 times 10 to the 24 kilograms of it in the sun. That's a lot of uranium. We know that 1 kilogram of uranium will release 9 times 10 to the 13 joules. So we can calculate the total energy that comes from the sun at 1.5 10 to the 38 joules. If we divide that by the output rate of the sun, then that would give the sun a lifetime of 12,200 years. Again, too short to explain the observed lifetime of the sun. So nuclear fission is out, even if we could concentrate all the uranium in one place to produce this energy, which of course we can't. So far we've seen several different possibilities for the sun to produce the energy we see, but none of them produce either enough energy or for long enough to explain the 4.6 billion year old sun with the amount of emission that we're getting from it currently. The one process that does seem to do that is nuclear fusion. That's where hydrogen is changed into helium. Well, how does that work? Well, you start with 2 protons, i.e. the nucleus of a hydrogen atom, and under high temperature and high pressure you collide them. When that happens, you produce a deuterium nucleus. There's an emission of a positron, which can go on to be annihilated with an electron and produce yet more energy, and a neutrino. If that deuterium nucleus then hits a proton, it can produce a helium-3 nucleus. That's 2 protons and 1 neutron, and results in the emission of a gamma ray. Then if 2 of these helium-3 nuclei collide, then you produce a helium-4 nucleus. That's 2 protons and 2 neutrons in the core, and the emission of 2 protons. This whole process produces a great deal of energy, and is called the proton-proton chain. It is believed to be the predominant method that the sun is producing energy currently, and will do for a long time to come. So how much energy can you get out of this process? Well, for that we have to go back to the formula E equals mc squared. Effectively, we are turning 4 protons into a helium nucleus. And we can calculate the mass of those particular components, and it says that we lose about 0.0285 atomic mass units. That is equivalent to a release of 4 times 10 to the minus 12 joules. So all we need is about 10 to the 38 fusions to be able to explain the energy from the sun. So how can this process possibly work? We're taking 2 protons which are positively charged and trying to smash them together to produce a helium nucleus. But protons have both got the same charge and should repel one another. So what we're really asking is, how does the nucleus of any atom hold together when it's full of protons, all with the same charge, and should be repelling one another and flying apart? Let me remind you of the electrostatic rules. Two opposite charges will attract. Two positive charges like protons will repel one another. Two negative charges like electrons will repel one another. So here we have a nucleus, a helium nucleus with two protons in it. What holds it together? It turns out there are other forces in play apart from electrostatics. So let's take a look at those. One is gravity, but gravity is very weak over short distances. It's great over long distances, but not short ones. There's another force called the weak nuclear force, which by its name implies that it's not a major player in this, so we won't talk about that. In blue here is shown the electrostatic force, which is repulsive force, and it operates over long distances quite well. And then there's the strong nuclear force, and no, it's not named after me, that operates only in the nucleus of the atom. If you can get these two protons close enough together, i.e. within that nucleus boundary, the strong nuclear force overwhelms any electrostatic repulsions and holds the particles together. So the nuclear bonding force is stronger over these short distances. And that's why you need high densities and high temperatures in the core of a sun to produce nuclear fusion. Because you want to start with the particles close together and then smash them hard into one another so they get within the nuclear boundary and the strong nuclear forces can hold them together. So what implications does this have as far as the solar lifetime is concerned? The Sun turns out to burn about 4 million tons of hydrogen every second. That would give the maximum lifetime of the Sun to be 16 trillion years. But that of course is a vast overestimate because not all of the hydrogen in the Sun is going to be used as fuel. But hydrogen is not the only fuel. When most of its hydrogen is burned up in the core, it will start burning helium. The Sun has been relatively stable in its emission over the last several billion years. How can that be? We can't stabilize a fusion reaction on Earth for more than a few seconds. Let's say the Sun's reaction rate increases for some reason. What would happen? Well, the temperature would go up. When the temperature goes up, the core would expand. That would create not only a lower density, but also a lower temperature. And so the reaction rate would decrease again. So the Sun is sort of a self-regulating nuclear fusion reactor. So now let's consider the opposite situation. Say the reaction rate decreases for some reason. The temperature of the core would drop and the core would collapse. Therefore the density would increase and the temperature would increase, which in turn increases the reaction rate again. So I think it's somewhat remarkable that this star can accidentally do for billions of years what we can't even do when we try very hard for a few seconds. The light travel time from the core of the Sun to the surface is about 2 seconds. But that's the light travel time in a vacuum, but of course the Sun is anything but a vacuum. So we'd have to consider the other formula, which is the velocity of light in a medium is the velocity of light divided by the refractive index of the medium. Even then it might slow the photon down a bit, but not very much. The concept that we're really searching for here is what's called the mean free path. And the mean free path is the distance travelled by a photon before it's interacting with the nucleus of an atom. In this case would be helium or hydrogen. What happens then is the photon is scattered in a random direction, either anywhere from forward to backwards. And so when it does that, it then hits another one and gets scattered, and so on and so on. And that means that we end up with what is called a random walk. This is a random walk calculation going from the red spot to the blue spot. And you can see that it has to go a very circuitous route to get to the blue spot. And when you take that into account for the solar radiation and the high densities in the solar interior, that trek can take up to 2 million years. So the sunlight we're seeing at the moment was created in the core of the Sun 2 million years ago. Some years ago, there was a problem associated with the Sun and its rate of energy production. It was called the neutrino problem. The flux of solar neutrinos measured at the Earth was too small for the reaction rate that the Sun should be producing its energy on. So we had two problems. One, a problem with the solar proton-proton model, or a problem with our understanding of the neutrino. And this was a source of contention between solar physicists and nuclear physicists for many years. Actually, about 40 years. It turns out there are three types of neutrino: the electron neutrino, the muon neutrino, and the tau neutrino. We discovered that neutrinos change their type on their flight from the Sun, and so we were measuring the wrong type of neutrinos. So I'm rather proud to say that the solar physicists won this argument over the nuclear physicists. So what conclusions can we draw from all of this? Well, the Sun produces its energy from nuclear fusion. The Sun produces most of its energy from nuclear fusion, the proton-proton chain in particular, in the core of the Sun. The Sun is a self-regulating nuclear reactor. The energy takes millions of years to escape from the center of the Sun and reach the surface. And the Sun has enough hydrogen fuel in its core to last another 4 billion years or so. In the next talk of this series, we're going to take a look at the evolution of the Sun. We're going to engage in some time travel, starting at the very beginning of the life of the Sun, its evolution onto and along the main sequence of the Hertzsprung-Russell diagram, noting at what point the Earth will become uninhabitable due to that evolution, and the eventual fate of the Sun in several billions of years' time. So until next time, stay safe and goodbye.